the marker will do something like this, because it is attached at the bottom of the back side of this block. So it will draw this type of pattern, that is, it is showing us the graphical relationship between displacement and time, and that is how we are going to get this graph, which is exactly what we just described, a cos omega t. Okay, now look at it. At time equal to 0, go back for the circular path. At time equal to 0, the object was starting from this point, that means maximum amplitude. At time equal to 0, maximum amplitude, and time equal to 1/4. Suppose total time period is t, 1/4, t by 2, 3t by 4 and t. Okay, so at t equal to 0, maximum displacement. At t equal to what? T by 4, we have the projection reaches at the center, so displacement is 0, that is why 0. And then when t is t by 2, then again maximum displacement, but this time this is on the opposite side, so minus t by 2. At 3t by 4, it is going back to 0, so we have 0 and then maximum. So that is how we have drawn the graph. This graph is similar to this graph, but we have just shifted this graph t by 4 in terms of time period. It has been shifted t by 4 in front, so this graph gets converted into sine graph. So SHM can be represented in both sine and cosine waves, doesn't matter. You can start with cos, you can start with sine, because if I start my particle from this point, the graph I am going to get would be of sine. If I start my particle from this point, the graph I am going to get would be cos. Now, velocity and acceleration can be calculated as functions of time and what? Time and displacement and velocity as well. How? We know the equation is x equal to a cos omega t. Okay, so now we don't want all this stuff. I hope it is very clear to you how to find on what projection means in relation to SHM. Okay, now we had an equation, x is equal to a, which is amplitude, cos omega t. I want velocity. What should I do? I'll differentiate it. If I'll differentiate, I'll get a, the cos of differentiation is minus sine omega t multiplied by omega. So minus omega a sine omega t. This is the value of velocity. If I want the acceleration, I'll differentiate it again. I'll get minus omega a sine omega t is cos omega t times omega. So minus omega square a minus a max, which is, yeah, they have done it in some different set. I'm going to tell you about it, but the simpler way is find x. We have derived x in the previous slide. Then finding velocity, which is differentiating the value of x, and then finding acceleration, which is differentiating the value of what? Differentiating value of velocity again. Now look at this term, a cos omega t. What is this? A cos omega t is x only. So minus omega square x. This is acceleration. So acceleration is directly proportional to negative of displacement. That is why this acceleration belongs to force, which is simple harmonic in nature, and it is opposite to the, because this is restoring force, this is opposite to the force applied. So this is what we have done. Acceleration is force upon mass minus kx upon m, or x is what? A amplitude minus ka upon times cos omega t. This will give me the same thing which we have just derived. These are the same graphical relationship for displacement, velocity and acceleration. How? When displacement is maximum, when the amplitude is maximum, that is just a, what will be the value of cos? What will be the value of theta? At theta equal to 0 degree, cos 0 is 1, so x would be equal to a. That means at 0 degree I am getting the maximum displacement. So put the value of theta in this equation, you will get velocity. What will it be? Sine 0 is what? 0, so velocity has to be 0. So for this thing, velocity would be 0. And again, for acceleration, I found this equation. Put cos theta equal to again 1 as theta equal to 0 degree, I'll get acceleration to be minus times displacement. So that is why acceleration is negative of displacement. So now you see how these three are related. At any interval of time, suppose displacement is 0, theta would be pi by 2. At pi by 2, that is this time t by 2, displacement is 0. But if I put 90 degree in sine, I'll get maximum. So velocity would be maximum when displacement is 0, and same is the case with acceleration. This is how acceleration, velocity and displacement are related with one another. Now Simple pendulum, we know about it. A simple pendulum consists of a mass at the end of a lightweight string. We assume that the cord does not stretch, it is unstretchable and its mass is negligible. Okay. Now whenever this pendulum moves, before I take you to that part, I want to tell you something more about simple pendulum, which is, remember when we did like few slides back, I am on the simpler pendulum, I don't want to show you that. Few slides back we did something what, when the block was at the highest point, it was having only the potential energy, and when this block was passing the mean position, it was having only the kinetic energy. Similarly, if I have my pendulum and this, let us say this is the extreme positions of pendulum, so it is swirling like this. Okay. So what we can see, suppose this is the ground position, here we have maximum height, here we have maximum height, that means all the potential energy here, which will be mgh, will be getting converted into kinetic energy, which would be half mv square, and the kinetic energy will get converted into back potential energy, which would be mgh. And that is why the place where we don't have any height is having kinetic energy, and the place where we don't have any velocity is the potential energy. So law of conservation of energy is still conserved. Now, in order to be in SHM, the restoring force must be proportional to negative of the displacement. Here we have, see, what are the forces acting on this bob right now? A weight, then components of weight. First of all, let's forget about components for now. Weight acting in downward direction and the tensional force acting in the string. Now I can draw two components of this weight, which is mg cos theta and mg sin theta. So see, this mg sin theta is directed inwards, opposite to the displacement. So force is minus mg sin theta. So that is why this is executing simple harmonic motion. For all small angles, the force is approximately proportional to angular displacement. That is why the time period is given by 2 pi under root m upon k. And for k, we have written the value mg upon L. And putting this value, we get the time period 2 pi under root L upon g. This is the derivation which we were talking about few slides back. Now, what are damped oscillations? If I draw a graph, suppose there is no loss of energy in this whole setup, or there is no loss of energy during that setup which we started with our this whole study from the block connected with the spring. If there is no loss in energy, so remember that block connected with a marker and marker drawing the whole graphical pattern. In that case, the oscillations energy will keep constant throughout the motion. But this usually never happens. There is always the presence of friction, there is always the presence of loss of energy. That is why these oscillations decrease in amplitude. That means the oscillations go in this way, that these are called damped oscillations. The amplitude keeps on decreasing. These are damped oscillations. Okay. So damped motion of an harmonic motion is frictional or drag force. It is, if the damping is small, we can treat it as an envelope that modifies the undamped oscillation. Okay. Now what are force oscillations? In which there is a constant driving force behind each oscillation. Suppose the pendulum is going from here to here but is stopping here. Okay. But that means if it is stopping here, this won't be reaching the maximum height again. It will be stopping somewhere here. If I am pushing it, every time it is coming here, I am pushing it with some force so that it reaches this height. That is how force oscillations are caused. It is backed by some external agency. Force oscillation has a Q factor. Q factor means quality factor. The sharpness of the resonant peak depends on the damping. This is called quality, and the sharpness depends on damping. If the damping is small, it is quite sharp. If the damping is large, the sharpness would be very low. Now, what are wave motion? Now we have completed the simple harmonic motion. Let's shift on to wave motion. What are wave motion?